It is fairly common for us to want to use a random variable to count the number of trials it takes until we get a set number of successes. So if we think about performing an experiment where we're repeatedly having binary trials, so either success or failure, we might need to succeed a certain number of times on these trials. And the question that we might be wanting to answer is, well, how many times are we going to have to perform this experiment until we achieve that set number of trials? If we want to use a random variable to capture this process, then we would be using a negative binomial random variable. So if a random variable counts the number of binary trials required until a set number of successes are obtained, then it is said to follow a negative binomial distribution. So what is the negative binomial distribution? Well, suppose that x is going to be a random variable, and the random variable is going to start at a value of r and then go up from there. Take every integer value past this value of r. The value of x is going to be obtained by counting how many Bernoulli trials are required until r successes are observed. And so if we want to say, how many times do we have to perform this experiment until we have 10 successes, then we're starting at 10, right? And so x counts the number of total trials required to obtain r successes. The distribution of x in this case is going to be referred to as a negative binomial distribution. So every negative binomial distribution is characterized by two parameters, p and r, and these are going to represent the success probability for each trial, which is p, and the number of successes required, which is r. Okay. If we know that x follows a negative binomial distribution with a number of successes equal to r and a success probability of p, then the probability mass function is known. And this is given to us by x minus 1 choose r minus 1 times by 1 minus p to the x minus r times by p to the power of r. And again, it can take any value starting at r and going up from there. Now, an important piece to point out about the negative binomial, which we can see from the result right here, is that if you take r equals 1, then we actually get the geometric distribution. Okay, so the geometric distribution is a special case of the negative binomial. And so normally we think about the negative binomial as actually requiring r to be greater than 1. If you take r greater than 1, then we can use the negative binomial, right, characterized up here. And otherwise, we're thinking about the geometric distribution. Okay. If you have the PMF, then we can also think about, well, what are the summary statistics here? And so the expected value is going to be given to us by r divided by p, and the variance is r times 1 minus p divided by p squared. So again, all of that tracks with r equaling 1, we get the geometric. When r is greater than 1, we have a negative binomial. So considering an example here, suppose that we have a 20-sided die and it's rolled until a 20 is observed 5 separate times. We're letting x count the total number of rolls that we take. So to start, what's the distribution of x? Well, in this case, right, we have a constant success probability. There's a 1 in 20 chance or a 0.05 chance that you roll a 20. And we're going to continue to perform this, either getting a success or failure, until we have 5 total successes, until we've seen a 20 5 different times. Okay, and so if we're going to be repeating an experiment over and over and over until a set number of successes, that's going to be negative binomial. Right, so x follows a negative binomial distribution, r is equal to 5, p is 0.05. What's the probability that x is equal to 100? And so in here, if we want to know the probability that x is equal to 100, what we want is we want to take the PMF and plug in 100 into this. And so that's going to be x minus 1, so 100 minus 1. Choose r minus 1, r in our case is 5, right? And then we take 1 minus our success probability, which is 0.05, to the power of x minus r, so 100 minus 5, times by 0.05 to the power of r. Okay, and then we can work this out using a calculator, and that will give us the actual probability here. Right, so using that PMF, we can get our probability that x is 100. And so if we actually plug into this, right, we plug in all of those values and work it out, and that gives us 0.009, right? So there's a 0.009 probability that we have x equaling 100. What's the expected value of x? Well, the expected value of a negative binomial is going to be r divided by p. And so r here is going to be 5 divided by p, which is 0.05, right? So we take 5 divided by 0.05, and that gives us 100. Finally, what is the standard deviation of x? Well, the variance of x is r times 1 minus p divided by p squared. Standard deviation is going to be the square root there, right? So standard deviation of x is the square root of that. We plug in r times 1 minus p divided by p squared. That gives us about 43.589. Okay, so in this case, we have a random variable that's counting the total number of trials that are required until we see 5 successes. That's going to be negative binomial. Let's look at another example here. Here we have a computer that is running a certain program, and the probability that it crashes on any given day is 0.1. Okay, so what's the probability that the third crash comes on day number 30? Okay, and so in this case, right, we're going to be repeatedly running this program every single day. Each day, there's a 0.1 probability that it's going to crash. Here we want to know, well, what about the third crash, right? R is equal to 3. And so here we're going to have x counts the total number of days. This is going to be negative binomial with an R of 3 and a P of 0.1. Okay, and we want to know, well, what's the probability that x equals 30, which is just the probability mass function with 30 plugged in. Okay, probability mass function is x minus 1, so 30 minus 1, choose 3 minus 1, right? And then we would have 1 minus 0.1 to the power of 30 minus 3 times by 0.1 to the power of 3. Okay, and so then we plug all of that into our calculator, and that will give us our probability here. So again, identifying that this is negative binomial makes it quite straightforward for us to work out the probability mass function here. We have x being a negative binomial with a 3 and 0.1, right? So plugging into our probability mass function, we get the probability is about 0.0236. So about a 2.4% chance that on day 30, the third crash comes. Now, how many days should you expect the computer to run until 10 crashes have been observed? So here, right, we're still dealing with a negative binomial, but no longer are we looking at r being 3. Here we want r to be 10, right? And so here, x is going to be negative binomial. The success probability has not changed, right? But r is now 10. Success probability is 0.1. And the expected value of x is going to be r divided by p. And so then we take 10 divided by 0.1, right? So how many days do we expect the computer to run? 10 divided by 0.01. Expected value of x is going to be 10 divided by, that should actually be 0.1 in this case, right? The success probability is not 0.01, it is 0.1. And so with that fixed, we see that the expected number of days is 100. So if Bernoulli trials are going to be repeated until r total successes are observed, then the random variable that counts the total number of trials follows a negative binomial distribution. This is again very linked to the geometric distribution, where the geometric distribution is the same thing as the negative binomial distribution if we take r equals 1. And so the negative binomial becomes the case whenever we need to get 2 or more total successes. Once we've identified that something is a negative binomial distribution, we know its PMF, we know its expected value, we know its variance, and calculations become a lot easier at that point.